Good afternoon, everybody. Welcome back to lecture number 3. Last time I asked you to review synchronous generators, SGs. I'm going to call it synchronous machines. Why? Because in 462, we assume that a machine is a generator or a motor in general, unless we know how it operates at. So for synchronous generator, let's say we have the salient pole. Say we have 4 poles. This is the rotor, this is the stator. Here we have windings. And here we have also windings. The windings go inside as coils. You agree with me? Now, for the synchronous generators, the rotor is the field winding, and the stator is the armature winding. So the armature is where the induced voltage occurs. For example, in the synchronous generator, when you move the prime mover using any sort of mechanical energy input, the magnetic field on the rotor would induce voltage on the stator, and you get your terminal voltage. For example, usually you get here A, B, C. You get your 3-phase voltage output from the stator. For a synchronous motor, you reverse the operation. You apply 3-phase, and then you spin the rotor at a synchronous speed. Here's the question. In EE360, we studied everything. We studied that the synchronous speed has to do with frequency and number of poles. But what we're missing is how to generate the magnetic field on the rotor. And this is what we are going to cover today. We have what we call the exciter. So how a synchronous generator works, for example, how a synchronous generator is, we really need to rotate the rotor at synchronous speed. Once it rotates at synchronous speed, the output terminal voltage is 3-phase output. But how in this rotor, this is a rotor, how are we gonna ensure that whenever this rotor rotates, along with it there is a magnetic field, a rotating magnetic field? How to excite this rotor? I told you in EE360, or whoever taught you EE360, that there is an exciter. Today we will study what is this exciter. So let's keep the problem simple and look at it from generator point of view. So again, 3-phase windings are wounded on the stator slots, keeping 120 degrees. Why? Because I have to have 3-phase output. It's not every cable is 120 degrees from the neighboring cable. It's the A winding is 120 electrical degrees away from the corresponding B. But sometimes you have A. Sometimes you have A, B, C, A, B, C, A, B, C windings. But the matching A with the matching B, they have to be 120 degrees. Get it? Now, there is a whole course that's not offered in KFUPM, but it's offered usually in graduate programs in some universities, where they teach them how to design these windings. What is the optimal size of the slot, for example? Where to put the magnets? How many poles? And it turns out you can't put whatever number of poles you want. There are standards that govern the harmonics generated from whatever you put. For example, how many slots in the stator versus how many slots in the rotor. There is a strict combination. One of the textbooks that explain this concept is, as I remember, is Intro to AC. Are we recording? Yes, we're recording. Alish, this row, please always monitor that we're recording. To AC machines by Professor Leppo. Professor Leppo, he was a professor at the University of Wisconsin, Madison. And this professor, he wrote a book on how to design every slot of the machine, how to put the windings on the machine, how to assign the diameter of the machine. It's a whole science. And every calculation usually is governed by what we call finite element analysis, FEA. So for you as a machine designer, we're not going to study in this course how to design the machines. We're going to study in this course how to drive the machine. So one of the drive techniques, as I told you, is how to excite the field in the rotor. So we have two types of synchronous machines rotor. We have the wound, and we have the salient pole. Now this is north and south. It doesn't mean there is an actual magnet here. It can be a steel that is magnetized. Get it? Sometimes we put permanent magnet. That's the easiest solution. The most practical solution, the more affordable solution, is to put is that we magnetize the bars themselves. So in the rotor, the magnetic field is generated either by a permanent magnet or by applying DC current to rotor winding. Why DC?
To electromagnetize the rotor.
But,
make the rotor magnet.
But what if I apply three-phase? I'm going to teach you that.
You have a يعني بيكون في تغيير واجد في المagnetic field فما بيكون عندك يعني.
You are right. You need a uniform magnetic field. Because if you have a uniform magnetic field and the uniform movement of that uniform magnetic field, you're going to predict how much voltage you're going to induce in the stator. So a uniform rotating magnetic field is what we are trying to do. This is one of the questions. This is one of my favorite questions in the exam. You have to watch YouTube to remember these questions. Is why we put DC current in the rotor winding. Why?
We want fixed magnetic field.
We want a uniform magnet. Uniform. It's not fixed. It's not, if the rotor is standstill, it's fixed. Constant flux. But because you're spinning it, it becomes a uniform rotating magnetic field. But it turns out that the excitation process is not that straightforward. Okay? And as I told you before, rotor is the field winding, and the stator is the armature winding. From now on until probably major one, we're going to talk about synchronous machines. So please, if you haven't done so, study 360 synchronous machine part, okay? It's a prerequisite. You have to, I'm not going to spend 1 or 2 weeks revising it. You have the resources, do it now, you have time, okay? For high-speed machines, usually number of poles is not that much. We want to have round. Why? Because the salient pole will cause air friction. But for the vast majority of synchronous machines, we have high number of poles, and because of high number of poles, the speed is slow. If you remember, the speed the speed of the synchronous machine is Ns is what? 120 F over P. You remember this?
Yes.
So F is the frequency of the electricity produced in the case of the synchronous generator. Or for a synchronous motor is the frequency of the current connected or the voltage source connected to the synchronous motor. Both are the same. So if you increase number of poles, the corresponding synchronous speed is less. Because the corresponding synchronous speed is less, the salient pole option is a better selection. Because I don't care. It's low speed. It doesn't matter if they revolve around the air at low speeds. The bigger the machine, the slower it becomes, the higher the number of poles, the more you're going to see its salient. For the sake of excitation, it doesn't matter whether it's cylindrical or salient poles. Okay? Now, as you can see, this is tens of hundreds of megawatts. This is just few hundreds of megawatts. So usually small generators or small synchronous motors, they tend to have the non-salient option, the cylindrical. How to excite the rotor? We already know from EE360 that in order to produce a magnetic field, in order to induce a voltage on the stator coils, I need a uniform RMF. What is RMF? This is one of the abbreviations. RMF is rotating magnetic field. So I need a uniform RMF in order for me to induce the voltage. On top of that, I need to spin the rotor. Before I spin the rotor, I need to make sure there is an excitation. So excitation is means of establishing the machine flux, the rotor flux. There are three ways to do it. And that's why you're taking this course. The first one is permanent magnet. PM is what? Permanent magnet excitation. So this is the approach that we use for synchronous motors in vehicles. Remember from last lecture I told you, Tesla, they use what type of machines? Induction machines and permanent magnet synchronous machine. So we expect number of poles in Tesla to be high or low? Low. Because it's going to be from this category. High-speed machine with cylindrical rotors, several hundred megawatts. This is for the case of the generator. But for Tesla, it's a small machine. So number of poles is less. So in Tesla, I don't need to have the other two types of excitation because I can put permanent magnet. The problem with permanent magnet is that they demagnetize over the time. How do they magnetize? Because the synchronous machine go into generation mode and motoring mode. Because of this shift, generating and motoring, it leads to faster demagnetization. It's not only that, in EVs they have so much high current from the inverter. This high current also causes demagnetization. Permanent magnets are not permanent. They demagnetize if you put them in high stress environments where high current, high friction, as well as the constant change in the flux, you demagnetize it. So it's not a solution that you want for 25 years. It's a solution that you can live with it up to 10 years. That's why if you look at EVs, you look at the, there is if I'm not mistaken, usually they say 10 years or maybe 200 mile or 200 kilometer. Usually you achieve it 500 kilometer, 500 kilometer, 1,000 or 10 years, you have to change the traction system. They have to put a new permanent magnet, they have to look at the inverter. So this is not practical. You can't go in a small generator and change it every 10 years. So that's why for generators, big application, we use either brush excitation or brushless excitation. So what is the brush? You remember DC machines, right? So in DC machines, you have the terminals where you have slip rings, right? So in synchronous generator or synchronous motor, you connect one of the slip rings. Of course, here we have the carbon brushes. This is slip ring. The circle is slip ring. The cubes are brushes. One is to the positive DC, one to the negative DC. How does that work? This is the shaft of the machine. Shaft is made of aluminum. Aluminum conducts electricity, صح? Aluminum is a conductor. Remember, transmission lines, high voltage are made of what? Aluminum. So if I connect a positive DC and a negative DC, for some reason the slip rings, there is a connection on rotor windings. Even if it rotates, I ensure that some of the windings are connected to DC all the time, half of the time. The other windings are connected to negative DC. This way, you ensure that you're exciting the rotor windings all the time using the slip rings and the brushes. And here you can have your DC source, maybe a small battery, or for a big generator, a small DC power generator. Same what we see in the lab. But the problem with it is the shaft rotates all the time, the slip rings rotate all the time, the brushes need to be replaced from time to time. So this solution is affordable and cheap, but it's not durable. So we use brushes and DC sources similar to the commutators for DC machine. Remember, you're just connecting DC to the rotor windings using the slip rings. Okay? Using the slip rings, you connect DC source, positive and negative, using two slip rings and two carbon brushes to the windings. The slip rings are 180 degree ring, and then there is a space, there is another 180 degree. They rotate with the shaft. Half of the time you connect it to positive, half the time you connect it to negative. They're mechanical devices. Any question about them? So I advise you to visualize them. There are some YouTube videos that explain how brush excitation works, and they show you how they rotate. But what is the disadvantage?
The brushes, they wear off.
Brushes, they wear off all the time. Okay? تمام شغال. وين ورقة التحضير؟ So, in order to connect the rotor winding in this figure, I need to, I have the shaft here. This is the shaft. I need to put slip rings here, positive, negative. And then some of the coils will get positive, some of the coils will get negative. And then I create the flux from positive to negative. Ultimately, I want flux lines from positive to negative. Any question? The moment I rotate these flux lines, what will happen? I'm going to have a uniform rotating magnetic field. Without rotations, are the flux lines moving?
No.
No. So the slip rings is, whenever I rotate the rotor, they maintain the DC polarity. Let's look at some pictures. So you can see how the slip rings work. This is the rotor, and this is how they are. This is construction of the rotor. This is how they look like. Slip rings. Honestly, this is mechanical engineering. But this is no, that's usually they look like that. There is bearings, there is mechanical components that maintain the DC. So fed through slip rings and brushes. This method is simple, requiring regular maintenance, etc. So are we going to use brush excitation all the time? No. We need the brushless excitation. This is the most preferred method. How does it work? Let me explain it now. So using exciter with rotating rectifier. This is one of the methods. We have rotating rectifier. Using exciter with rotating rectifier. What do we need? We need a separate AC source. Is it easy to secure an AC source in a plant or DC source?
TCS.
No. In building 59, what do we have? DC or AC? AC. AC, substation. AC. So usually DC power supplies are specialized by request. But every room has AC. Not every room has DC. So using this method, we're gonna have, imagine with me, this is the stator. This is the rotor. Okay? We're using block diagrams. So we connect the stator at the beginning with a three-phase input. So we supply in these three windings low input current. Then before it goes, I'm sorry, we don't supply, we supply the three-phase to, what is this device? This device is rectifier. It converts AC to DC. So now, three-phase input low current, we're gonna have here what? DC low current. And we apply it to where? To the field. Again, we apply three-phase, small three-phase low input current, 110, 120. We put it through a rectifier, and then here we have a DC. We apply this DC on the stator winding. Before any movement, before anything, at the beginning. Then the rotor windings we will start spinning them. The rotor windings are cutting the constant flux lines from the DC, from the stator. Yeah, I know ultimately it's an AC machine, but we're applying DC at the stator. We move the rotor would cut the constant flux lines. So we're gonna have an induced voltage in the rotor. That output, that induced AC voltage from the rotation connected to another rectifier, three-phase rectifier. Get it to DC. Then you get it to DC, you feed it again to the main rotor windings. So you may use some of the windings in the stator for excitation, some of the windings in the rotor, and the majority of windings you apply to them this constant DC current. This way, I did not need to get an outside DC source. You see the trick?
Yes. Like feedback?
Not a feedback, it's cheating method. What we did is we applied in some of the windings small DC, small AC. Rectified becomes what? Small DC. Hook the small DC current in the stator winding. What will happen? We're going to have constant magnetic flux. Start spinning the rotor. If you start spinning the rotor, If it's a motor, because the car is moving. If it's a generator, because there is a prime mover. You are going to have an induced voltage on the rotor windings. Apply them to what?
rectifier.
To a rectifier. When you apply them to a rectifier, you get what? DC. This is the field current DC. Then you apply it to a main field, the main windings. Then we satisfy the purpose of applying DC current to rotor winding. So what did we use? We used the stator to generate, to induce the voltage in the rotor, that induced the voltage back again to the stator. You think this method is doable, but what if I do not have an AC supply at all? Yes, what's the question?
الحين current you apply الاوتبوت حق الفاينل اوتبوت على الروتر نفسه صح؟
No, your final out, okay, let's say for a generator, generator.
طيب.
For a generator, you get small AC, you rectify it.
اوكي.
You apply it at the stator. You have constant magnetic flux. هذه constant magnetic flux induces nothing على الروتر. Start spinning the rotor.
روتر connected to nothing حاليا.
احنا generator. فيو need the prime mover. ديزل engine يحرك الروتر. Rotor would cut the flux line, صح? Because the rotor cuts the flux line, it will have induced three-phase voltage. Apply this induced على another rectifier inside the rotor. You get the DC. This DC applied على المين, على all the other windings. You have 100 windings. You can use maybe 5 for a DC, 95 for an AC. It's by design.
المين ويندنج قصدك فيها الستيتر ويندنج.
No, rotor.
روتر ويندنج.
روتر وايندنج كل واحدة لها وايندنج فيها روتر وفي ستيتر. This is not an induction machine. Induction machine الروتر ما في له وايندنج except very small type. The synchronous, both of them they have windings. Then apply that DC على main winding and then you get your three-phase output, high power, high voltage. So we started with small three-phase input, we got at the stator what? Three-phase output. Then you start moving the rotor, now it has DC, you get the ABC outside, the terminal voltage. So the trick here is apply small DC from a small AC source, get back a bigger DC.
طب انت اوريدي اصلا حاطط سمول اي سي على الستيتر. فقاعد سبلاي بتاخذ نفس الوقت كيف؟
In some of the windings, not all of them. You use some of the windings as exciter. It's part of the exciter. You don't use everything. So maybe you have 6 terminals, 3, 4, or maybe you have here DC, 3-phase, and you apply 3-phase inverter. You need maybe 2 windings DC. With 2 windings, they propagate all the series, and you have how many conductors per loop. We're not going to go into how they do it. Again, this is the winding course. But the concept here is you apply small 3-phase, you rectify it, on the rotor you generate another 3-phase, you rectify it, now you have the DC in the rotor. Because it spins, it supplies what? The 3-phase output. So, are we required to memorize this block diagram?
No.
Yes.
Not memorize, but understand, okay? If you think this block diagram is simple, let's look for a one that uses the pilot exciter. The pilot exciter with rotating rectifier. Here we don't need AC source. Here we need a small AC source. So the direction of movement is this way. Here, we don't need AC source. What if I cannot apply a small rectified DC على state? What if I? One method they use is they use the pilot exciter, and this curve begins from here. So in the pilot exciter, We get now a permanent magnet, but does it have to be a big permanent magnet? No, it's a small permanent magnet. Why? Because I need to excite, I put it in the rotor, I start spinning the rotor. So there is magnet on the shaft connected to a group of coils. This magnet rotates. So it generates the flux lines and it rotates. It induces a small three-phase AC على الستيتر. So this is what you call it, pilot exciter armature. A group of winding, we put them in a way على الستيتر so that when I rotate the permanent magnet, the small permanent magnet exciter, they induce a small AC. So now I reach here. I now have low current three-phase. If I rotate the permanent magnet على الروtor, if I rotate it, I'm going to induce small three-phase على الستيتر. A group of conductors, we call them pilot exciter armature. Then I have the small three-phase AC. I put it into a rectifier. So this rectifier is actually this rectifier. Now I'm at the stator. I apply three-phase AC على الروtor with another group. We call them the exciter armature. Then we rectify to the main field. Once we rectify the main field, I have big DC على الروtor. Then I can get my three-phase output على السynchronous generator. So here we went rotor, stator, rotor, stator. Here we went stator, rotor, stator. Now these are technologies. These are maybe devices that you can buy them, or systems that you buy them ready. You probably need to put them. So you can buy exciter for your generator. And then they come and they put it for you. Why we did all of this excitation process? Because I want to solve my main problem. What's my main problem? I want to have a DC field in the rotor. I want this DC to induce the main AC. 360, we only look this way, صح?
Yeah.
360, we only have, I told you we have DC rotor, induces the voltage at AC. But how to get that is the story that I explained today.
So we don't use batteries.
No, you don't use batteries.
Mm.
Some of them they use batteries. Some of the application. Battery is like a permanent magnet. Small batteries. Battery is not a battery, it's a power supply. This is you use batteries for brush excitation. For brush excitation, using brushes and DC source, which is a small battery. But let's say you don't have a battery, what should you do? You use the brushless excitation, which is the most preferred. اشرحها مرة ثانية؟ على السريع؟ Okay.
This for the brushless excitation, we can also use a DC source, correct?
I don't think so. For brush excitation, you have to always to begin with AC or permanent
But
magnet.
because we rectify it immediately, so why does it need to be AC?
You can do it, but I don't think it's a common practice. How are you going to keep it connected?
Mm.
The beauty of rectifier is that the inverters are put inside the machine. The problem with the DC source is you need polarity, positive and negative. How to dig deep into these systems, you have to look at the manuals of every product, but the concept is usually the brushless excitation is the most common. So exciting the machine is not an easy task. So let me begin again one more time. The main problem we have with synchronous machine is what? We need DC current in the rotor. This is the problem. We all agree, صح?
Yeah.
Because the moment I have DC, if I spin it, I'm going to induce AC voltage على stator, problem solved. I get my output.
The mechanical output, right?
The
For motor.
for motor is another story.
Oh.
For the motor, you have to supply the three-phase. You have to supply the signal, and then your rotor is rotating. But even though it's rotating, it still has. Usually, for synchronous motor, we put permanent magnet. خلاص, problem is solved. For synchronous motor, always think of EVs, because I am not aware of synchronous machines used in industry except synchronous motors. Most of the motors are small. There is no giant motors, but generators are giant. So for motor, you just use permanent magnet excitation. Problem is solved. As a matter of fact, there are designs that do not need permanent magnet. They create the magnet in a triangular using the reluctance of the machine. Call them switched reluctance. You don't even have a magnet. So the innovation in motors is now, we don't need magnet. But for the big generators, they need brushless excitation. They don't like magnets. Magnets are not favorable in generators. Because when we put a generator, we put it for 25 years. A generator is a big investment for a utility. If a generator is built today, it should last at least 25 years. Most of the generators would exceed 50 years. So it's a big investment. That's why having brushless excitation is a worth investment. And I told you, we cannot use permanent magnet. We may, if we have a small auxiliary AC source, we can apply three-phase input current, rectify it, get small DC على الستاتر. Because the rotor is moving, it induces a small three-phase. A rotor rectified, get the DC. While it's rotating, the main windings are rotating, get the output three-phase. What if I can't produce that? I need to connect that to the permanent magnet on the rotor. Because the pilot exciter, we have the pilot field, we induce the AC due to the rotation axis. So every time the stator either to induce in the rotor or the rotor is inducing on the stator.
الحين دكتور بعد ما في الدايجرام الأول
هذا حفظ خلاص.
الدايجرام الأول بعد ما يصير في دي سي طلع دي سي من الروتر أقدر أشيل الانيشال اي سي اللي
No, it has to be connected all the time.
ما أقدر أشيل حتى طلع.
They put it inside cases. They put the inverter in a casing. They put everything inside.
The electronics we discussed is for generators only? Oh.
Yeah, this is for generators. Because synchronous motors, remember Tesla, they use permanent magnet. They can replace it in 10 years. No car would stay more than 10 years. So for permanent magnet, we use it for motor. For generators, you use brushless excitation.
ممكن ترجع للجولة دكتور؟
The one that needs AC?
الحين احنا قلنا نحتاج دي سي صح؟ دي سي.
Okay, where we need DC. This is what we need. This is the main problem. This is the main need. The main need is we need to have a DC current flowing in the majority of the rotor windings. To get that, you need to have a small AC على الستاتر, rotate the rotor. Stator is always fixed. You induce on the rotor an AC, but this AC is small. You rectify it, you get what? Small DC. You need small DC. Small enough. Then you get the three-phase out.
يعني اللي يدخل على الروتر اي سي ولا دي سي؟
The rotor is not connected to any external power source. Your input to that system is a small three-phase input current and a mechanical input على الروtor. You don't put في البرش excitation, your input على الروtor is a DC source through slip ring. No rectifiers. But I told you this method is not durable because of the brushes. So your input for the brushless excitation, the most preferred method, your input is a small three-phase, you get it maybe 120. This is small for a 10 kV generator. Okay? So any question? It's time to ask. How I'm gonna ask you in the test? I might ask you plot the signal. Plot the signal here, point A, B, C, so you should give me, and I might give you values, for example. Maybe I give you 3-phase, maybe 110 kV RMS. What's the output of a rectifier? It's gonna be a constant voltage. But we will practice, maybe in the homework. Maybe I'll give you a homework problem. Is it clear?
Yes.
So all of you know now how exciter works in synchronous generator? Okay, awesome. So we have 5 minutes left. Let's revise a couple of concepts. If we increase number of poles or increase the speed of the machine, we change the frequency output. So F has to do with the electrical frequency in the terminals of the stator. N is the mechanical speed or rotor speed, synchronous speed, and P is number of poles. We remember this. We also remember that the induced voltage is 4.4 times the frequency times the flux times number of turns in each phase times a constant, we call it the winding factor. So the induced voltage on the stator, if you want to change it, you either have to change the frequency, but for synchronous generator, the frequency is controlled by the speed, or you change the flux, or you change N, which is number of turns in each phase, or the winding factor. These two variables are geometric, صح ولا لا?
Yes.
So these are geometric, it means I cannot change them unless I disconnect the machine and rewind the machine. We're talking about the stator winding. The stator winding. So K is a winding factor. If you want to know more about winding factors, I advise you, so you're level 4 now. It's time to explore more knowledge. Professor Lipo textbook. If you're interested, I can give you a copy of that book. Digital copy. Okay? So, the moment you talk about constant K in machines, they usually are calculated empirically, and there's empirical formulas. Usually it involves sine or sine h because it's circular rotation.
So
Yes.
EF is our target output from the generator, right?
Yes. EF is the induced voltage on the stator. And you control it, so you have only two control, either increase the speed or increase the flux.
الحين دكتور انا هنا في التيرمينال بوكس حق السينكرونس ماشين بيكون في عندي 6 تيرمينال اوكي مثلا.
No, usually 3. الاكسايتر عنده تيرمينال لحاله.
التيرمينال الثاني لحاله مشبوك على نفس شو اسمه.
No, different
على نفس
windings.
الوايندنج.
No, different. It doesn't make sense to have the same winding for small current or high current.
بالضبط.
Small, like you pick certain windings and you put them in the system, and you know that these are for the exciter. And remember, in windings, the coils are insulated. So they don't, if they touch each other, it's like two cables that are insulated touching each other, no problem. That's what we mean. So for you to control the voltage, usually most generators, they just increase the speed of the machine. So if you increase the speed, it means you increase your mechanical input. But there is another way by changing the excitation flux. How to change the flux? Using these methods. You either increase, make the permanent magnet bigger, or if you have a small AC, make the AC high. Or if you're using brush excitation, make the DC source bigger. So bigger the source, bigger the flux. But that's why if we use pilot, that's why one of the things is we prefer this approach or that approach is we can control using AC or permanent magnet. It's easier than controlling things using the DC. Okay? And remember, magnetization curve is if I increase the field current, I increase the flux. If I maintain the speed the same, I also increase the induced voltage. So it turns out that the relationship between them is linear, but I have a point of saturation. Do you want to operate at the saturation point?
No.
So you always operate just before the knee. You always operate just before the knee. That's very important concept to remember from EE 360. So time is up. In summary, if I bring you a fake quiz next week, I'm going to ask you to draw the block diagram. Those block diagrams are very important. They're very useful. There is a couple of videos on YouTube talks about the exciter. I highly recommend you to watch these YouTube on the web. But hopefully by today, I want you to know that in machines, in 360 we only showed you this part. But there is too many parts. And one thing we can see is power electronics is used. Rectifier is a device that converts AC to DC. Okay? Any other question? Concerned about the course? Okay, what is the attendance? الله يعطيكم العافية بالتوفيق. Feel free to leave. Thank you.